Section 5, the scoreboard. The scoreboard is perhaps the most interesting component in our entire OOP test bench. But because it's so design dependent, it's not easy to find a concrete working example of a scoreboard in the technical literature, even for a digital design under test, let alone an analog one. So one of our goals in this tutorial webinar is to present a working scoreboard example for our programmable analog bandpass filter. The job of the scoreboard is to compare the actual filter output versus the expected filter output for each transaction and to record and display the discrepancy. Earlier in the simulation run, the driver and the monitor have put their respective same tagged data packets into the mailboxes, sending them up to the scoreboard. So it's now time for the scoreboard to get those data packets and, based on the data, do a compare. But to do so, it needs some kind of reference model describing the DUT. For a digital design, the reference model might be a transactional model written in C++, or it might be a mathematical algorithm in MATLAB, or it could even be a previous version of an RTL design. In our case, the golden reference model is an array. It's an array consisting of 8 lookup tables, one for each of our enumerated modes. So the scoreboard will call a function selectTable based on the current mode and return the correct lookup table, one of the 8, into a scoreboard variable named goldref. That's goldref singular. As far back as Verilog 2K, the language began to support arrays, unpacked arrays, whose elements could be of any data type. And so here we have an array named goldrefs, plural, consisting of 8 lookup tables. Each lookup table, as we'll see, is typed as an associative array. And so our selectTable function takes in the current mode, uses a case statement to find a match, and here we have the backslashed mode names, including a trailing space, and it'll return the element of goldrefs, in this case the 0th lookup table, corresponding to that mode. So here is our lookup table held in the variable named goldref, ready to be scanned. Here's a closer look at that associative array, one of the lookup tables, the one for mode 0. In computer science, an associative array is defined as a collection of key value pairs. And we found this very convenient because it would even support frequency response data where the frequencies were not necessarily contiguous, consecutive. And so here the key is an integer frequency in kilohertz, and the value is a real voltage expected to be output by the DUT. So for example, for an input frequency of 12 kilohertz in mode 0, the DUT is expected to output a sinusoidal amplitude of roughly 56 millivolts. These are large tables, over 100 lines, so we found it convenient to backtick include them as header files within the package called gold package that is imported to the scoreboard. How did we generate each lookup table? Well, we ran a linear AC analysis in HSpice, which generated a .lis file, a text file, which included this large table of frequencies versus voltages in millivolts. Then we wrote a Linux-based awk script to convert this data line by line into a SystemVerilog associative array of correct syntax. And here you see the keys and values. And in SystemVerilog, we can use associative array literals to assign the contents of the entire lookup table at once inside a ticked, curly braced, comma separated list. And so we basically converted raw HSpice data into a syntactically correct SystemVerilog associative array. Now we're ready to scan the lookup table. We wrote a function called goldVout. Given the key, the integer frequency, this finds the closest match and outputs the expected real voltage, in this case 56 millivolts. So it scans the entire table using a for each loop and looks for the smallest delta and returns the closest match. And on this last slide, we're seeing an excerpt of the Scoreboard Transcript. Here we're showing just one transaction. Transaction 15 happened to have the worst case discrepancy. And so we're using the, as we saw in section 2, the peak-to-peak amplitude measurement primitives to generate the expected filter gain. And we're calling goldVout, a scoreboard method, to generate the expected gain at this particular frequency of 84 kilohertz. Notice they're pretty close. So during this entire run, the worst case discrepancy between the X model value for the filter output and the HSpice value was less than 2%.